Okay, here we go again with the homework. I'm on page 81, starting at number 80. We have an initial velocity, we have a final velocity, we have a period of time that we change our velocity and we're trying to find the acceleration. We can use VF equals VI plus AT. I'm going to solve here for acceleration. You plug in your numbers and you find that the acceleration is equal to 8 meters per second squared. I'm sorry. Okay. Number 82. We're looking at a graph here, and in order to find the acceleration at each moment, you're just going to take the change in velocity divided by the change in time. So in the first case, you're changing 30 meters per second over 5 seconds. In the second one, you're not changing any value of velocity over that period of time. For C, you're changing negative 10 meters per second because your velocity is decreasing. And then for D, you're drastically decreasing your velocity by 20 meters per second over a period of 5 seconds. And you can see I've calculated the acceleration for each example. For number 84, we have an initial velocity. Don't get freaked out by the scientific notation there. It can certainly be scary, but have faith in your calculators. We're given an acceleration, and we are given a time. That's 1.5 there. We can use the equation VF equals VI plus AT. Here's the math. The velocity final, 7 times 10 to the 4th meters per second. Number 86, supersonic jet. We're given an initial velocity. We're given an acceleration. We are given a period of time for that acceleration. The question is, what is the VF? Looking at our variables, the best equation to use is VF equals VI plus AT. Plug in the numbers here for you, and we are on our way. Part 2 says to express the answer in terms of the speed of sound. So basically they're just saying how many times the speed of sound is the velocity of the airplane. So you can divide the velocity by the speed of sound, and we get that it is 1.83 times the speed of sound. Another way of expressing this is Mach 1.8. So for example, if a jet is going Mach 3, it is going 3 times the speed of sound. On to number 88. Our dragster, we're starting from rest. We're given the acceleration. We are given the distance. It's asking for the final velocity. The best equation to use is VF squared equals VI squared plus 2AD. Rearranging the equation for VF here for you, and then I'll plug in some numbers. And we are on our way. Number 90, we are given an acceleration. We're slowing down. For part A, we're given an initial velocity, and it wants to know how far is it going to go before it stops. So if we're stopping, our VF is going to be 0. The equation to use here is VF squared equals VI squared plus 2AD, because that's what we're working with in terms of variables. Plug it in, and you can find the distance it takes to come to a complete stop. For part B, it's asking how many meters it will take to stop a car going twice as fast. So I just doubled the VI there. 55 times 2 is 110. We're really using the same equation because we're solving for the same thing, the distance it would take to stop. And the answer is 550 meters. Number 92, we have an airplane. We're given the initial velocity. We are given the final velocity. We're given the time here. I'm going to go ahead and find the acceleration because that would help us out. So the acceleration is the change in velocity divided by change in time, so it's 1.83. I'm going to plug it into this equation here, VF squared equals VI squared plus 2AD, rearrange it to solve for displacement. let's put some numbers in there for you. And there we go. How about 94? This was a tricky one. If you don't get it, I certainly don't blame you. This is a real head scratcher. I'm going to do it in two different colors here. You can see the speeding car in red, and then the police car in. Let me pause this for a second. I'm going to pause the action. Up top, I put the speeding car in maroon there. The velocity of car A, I'm calling the speeding car car A. Velocity of car A is given. The acceleration is 0 because it's not changing its speed. And then I put the police car in purple. The velocity initial of the police car is 0 because we're starting from rest. The acceleration is given. And the question is asking for the final velocity of the police car. So in this situation, you have too many variables and you don't have an equation that satisfies what you're looking for. So the best thing to do is to find a variable that might be common between your two different parts here. So I'm gonna let the video continue to play. And I'm going to write out the displacement equation for the speeding car, the car in maroon. Plugging in some numbers here for the displacement equation for the speeding car, we see that the acceleration portion cancels out. Now I'm going to write the same equation for the police car. We're starting from rest, remember. So the initial velocity portion cancels out. Let me pause the video there. So I've just written the same equation for both the speeding car and the police car, and I canceled out in yellow the portions that go to 0. But the question is asking for the exact moment when the police car catches up to the speeding car. At that moment, the displacement is equal, because since the police car began his journey, they've gone the exact same distance. So if the displacements are equal, we can set them equal to each other. And that's exactly what we're going to do. We're going to set one displacement equal to the other because they are the same in magnitude. So here's the work. I'm setting that top value for displacement of the speeding car equal to the displacement of the police car. So you got some t's that cancel out, and then I solve for the time there, and I get a real value. So now I know after 8.57 seconds is when the police car catches the speeding car. Now I'm just going to plug that t in to find the velocity final of the police car using our vi plus at. There's the work, and we can get our final velocity of the police car. Number 96, we're in free fall mode now. We're dropping a penny. The question is, if the down direction is positive, what will be the acceleration of the penny? Well, if the down direction is positive and you're speeding up in the down direction, your acceleration must also be positive. Because anytime you're speeding up, the sign of the direction and the sign of the acceleration must be the same. Number 98. Your velocity initial is 0 because you're dropping it. Your acceleration is gravity. The time is given. The question is asking for velocity final. We can use Vf equals Vi plus At to solve this. Solve for Vf, and there you go. Next question is, what is the displacement during this time? Well, we can use this equation. D equals Vt plus 1/2 At squared. The first term goes to 0 because there is no initial velocity. So we just have the 1/2 At squared. Plug in the numbers there for you. And we have a negative displacement because we're going down. Okay, question number 100. We're throwing a ball downward, so we have a initial velocity. I should have put a negative in front of that. We have a distance, displacement rather. Acceleration is gravity. It's asking for velocity final. Vf squared equals Vi squared plus 2Ad. Rearrange it for velocity final. Plug in some numbers. And we are on our way. Okay. The final question, 102. We're given a time, and let me pause the video here. We also I put time sub 1/2 because I noticed the question was asking that you throw a beanbag up and then it comes back down. Anytime you have an up and down question, it's likely that you're going to have to divide the time in half to just look at half of the trip. So I went ahead and defined the half of the time while I was at it. Let's keep on going here. The acceleration is gravity. And the distance, it's asking, let me pause it again here, it's asking for the distance that it goes up into the air. So I put d sub 1/2 because it's half of the total trip. Right, because the displacement for the whole trip would be 0 because you're throwing it up and catching it. So d sub 1/2 refers to the displacement that it goes when it just gets to its highest point before it returns back to the ground. Okay, so we're going to use Vf equals Vi plus At to solve for that initial velocity. So I'm doing it backwards. I'm solving part B first. I want to find that Vi because I can easily do that in the one-step equation. There's our initial velocity that we're throwing it. Now I can find my displacement using that initial velocity. Again, I'm solving for d sub 1/2 here. I sort of I forgot to continue writing d sub 1/2, but our displacement for half of the trip, when it just goes up into the air, is 5.93 meters. And that's the end of our homework. I want to remind you to help each other out. You know, this is hard. This is not easy, and it can be very stressful, and you can really get down on yourself, and you can really get frustrated. But please use each other as a resource. Use me as a resource. No one gets left behind. We're all in this together. Keep at it. You guys are doing really great work.